Welcome to lecture 29. In this lecture, we will continue our discussion on parallel operation of synchronous generator. Now, in last class, we have seen a numerical to understand how the load is shared. In this class, we will see how to connect two generators in parallel. So before we go into a synchronous machine, let's look at a simple case of connecting two DC sources in parallel. Let's say that this is a DC source and it have an internal resistance R. It is connected in parallel with another DC source having an internal resistance of say R2. This is R1, this is R2. Now say if this is 3 volt and this is 5 volt, what will happen? A current will circulate here like this from 3 volt, from 5 volt to 3 volt. A part of the current that is coming out here will have two parts. One will go like this, another will go like this. It will circulate through this. Why this happens? This happens because the potential of the two voltage sources are not same. Let's look at a case where the resistance of the sources are 0. That is, if we consider an ideal voltage source, then the resistance of a voltage source is 0. So, let's say that these are two voltage sources having 0 internal resistance. It has a voltage of 3 volt, it has 5 volt, it has a voltage of 3 volt. Now, between these two sources, there is a difference of 2 volt and the resistance of this is 0. Why I am saying that the resistance is 0? The reason is that I am saying these two to be ideal voltage source, and an ideal voltage source has 0 internal impedance. So there is no resistance, there is a voltage of 2 volt, there is a difference of 2 volt, so infinite amount of current will flow here. Infinite amount of current will flow. So connecting a voltage source in parallel requires that the voltage of the two sources should be equal. If it is ideal source, it has to be exactly equal. If it is non-ideal source, then we'll try to keep this as close as possible so that this circulating current is small. Now the same concept can be applied to a synchronous machine. In a synchronous machine, we have, if we want to connect two synchronous machines in parallel, and if we want that the circulating current here to be minimum or 0, then let's say that this is EF1, let's say that it is EF2, then these two voltages should be equal, or if equal is not possible, then they should be very close to each other. So the concept of connecting two DC sources in parallel and connecting two AC sources in parallel, or connecting two synchronous machines in parallel, is same. The concept is that the voltage should be same. Now when we say this for an AC source, when we say that two voltages are same, say this voltage is EF1 sine omega t, omega 1 t plus phi 1, and say this voltage is EF2 sine omega 2 t plus phi 2, and if these two has to be equal, then this one should be equal. What does it mean? It means that the magnitude of the sine wave, then that is a sine wave looks like this, the magnitude of this sine wave should be same for this source as well as for this source. Then we say that this omega, what is this omega? This is the frequency of the AC. The frequency of these two should be same. And what does this phi indicate? It shows the phase shift, that is how much if I say that this is time t equal to 0, then how much is this shifted either in this direction or in this direction? That is the starting point of this with respect to t equal to 0. This is the phase. So if two AC voltage has to be same, then we need to ensure three conditions. One, the magnitude of the sine wave should be same. The frequency of the two sine waves should be same. The phase of the two sine wave should be same. So to connect two synchronous generator in parallel, we have to satisfy these three conditions. What are the conditions? The magnitude of the voltage should be same, the frequency of the voltages should be same, and the phase of the two voltages should be same. Now let's look at a condition of connecting a synchronous generator to a infinite bus. Infinite bus can be considered as the second synchronous generator. Here we are showing two AC sources. This is my synchronous generator and this can be considered as an infinite bus. What is an infinite bus? Infinite bus means there are many generators that are connected in parallel, and as a result the voltage and the frequency of that source is constant irrespective of variation in the load. So let's consider that this is a synchronous machine and it is connected to a infinite bus. This is my synchronous generator that we are talking about, and this is the infinite bus. We are representing it as V. So let's say that this is E of F, this is V, and we have a switch here which is nothing but a circuit breaker. When we are satisfied that this E is equal to V, when we say E equal to V, here we do not mention about the phasor value. We are talking about the instantaneous value. It essentially means that all the three quantities, that is the magnitude, the phase, the frequency, all these three are same for E as well as V. When these three conditions for this E and this V are equal, then we will close this switch, and then this generator will get connected in parallel with many other generators that are already there in the circuit. An infinite bus is nothing but many such synchronous generators connected in parallel. So there are many such synchronous generators that are connected in parallel, and we are connecting one more to that. This connection of many synchronous generators in parallel is known as infinite bus. So we will see how to connect one more generator to this large number of generators that is already connected in the system. So what we have understood till now, we have understood that to do this, we have to ensure that the instantaneous voltage of this source is equal to the instantaneous voltage of the infinite bus. Now let's see how to do that. First of all, we have to ensure that the magnitude of the voltage here and the magnitude of the voltage here are same. How it can be done? First we need to understand that before we ensure that this switch is open, this switch is not closed but this switch is open. So there are three lines here. We measure the voltage of this using a voltmeter, and we measure the voltage here with respect to a voltmeter. If the voltage here and voltage here are same, then it is okay. If the voltage are not same, then how to change the voltage of this? Let's see what is the expression for this voltage. E of F is equal to 4.44 phi ft. This is the expression for the voltage generated by this. Now if we have to alter this voltage, we can change this or this, any one of this, but we cannot change this because this is the number of turns, and once we make the machine we cannot change this. So either we can change phi or we can change F. Now if we change F, then along with voltage the frequency will also change. We don't want to do that. So to change the voltage, what we have to do? We have to change flux. How to change flux? If you remember, in a synchronous machine there is a field winding which is connected to a DC excitation, and there is an armature in which the this symbol is for DC machine, for AC machine this symbol is not there. So this is a synchronous machine where we have a field winding where we give a DC supply, and here we get the induced EMF. So if we change the current in this circuit, that is if we vary this IF, then EF will vary. So to control the terminal voltage, or sorry, the induced EMF here, we will vary the field current of the DC machine, so of the synchronous machine. The DC current of the field we will vary to control the voltage. We will not control the speed to control the voltage. The next part of the question of the problem is to control the phase and the frequency. Now, to control the frequency, what we can do, we can increase the input to the turbine. That is, if we increase the speed of the turbine by a governor is nothing but the speed control mechanism of the turbine, then the frequency will increase, or if we decrease that, the frequency will decrease. Now the question is that who will tell me whether I have to increase the frequency or decrease the frequency? Let's say that our frequency is 50.1 Hertz. We can measure it with some meters. This we can do. Now, what is the grid frequency? This is the frequency of this machine. What is the grid frequency? The problem is that the grid frequency is not constant. It can be 50 Hertz and it can be 49 Hertz. It can be 51 Hertz. It will vary continuously depending on load. So even if I adjust it to 50.1 Hertz, by the time I adjust it, the frequency of the grid might have changed. So it is not a very good idea to measure the frequency and then adjust the machine. It takes a long time for a synchronous machine to reach a speed because of the inherent delay that is there in the mechanical arrangement or in the turbine. So if you say that get it adjusted to 51 Hertz, it will take some time for the machine to go and get stabilized at 51 Hertz. By that time, the grid frequency might have changed. So it is not a very wise decision or a wise logic to measure the frequency and adjust it. One more problem is that even if you adjust the frequency, how will you adjust the phase? So we have to simultaneously adjust the frequency and the phase of this voltage with respect to this voltage. That is the phase and frequency of the incoming generator with respect to phase and frequency of the infinite bus. To do this, there is an instrument that is called a synchroscope that is extensively used in substations. However, what we will discuss in the next class, not in this class, the next class is called a three-lamp method. Though three-lamp method is not used anywhere, but still it gives a good idea about the operation of the machine. That's why we will discuss this. If you ever go to any substation, you will find that they use synchroscope. But what we will learn is the operation of or say the concept of a three-lamp method, because it gives a better understanding about what is happening. So we will conclude this lecture here. Before we conclude, let's look at one very simple thing. If we have a voltage V like this, and if we have a current like this, we call this as a phasor diagram. Say this is voltage, this is current. We can draw a phasor diagram because this voltage and this frequency, this current are at same frequency. That is, we have a AC source like this. We draw a circuit like this. Say this is my V and this is my I, and we draw a phasor diagram like this. The reason why we can draw a phasor diagram is that both of them are in same frequency. If this is at 50 Hertz, this will also be at 50 Hertz. That's why we can draw a phasor diagram like this. But say I have two voltage sources So this is at 50 Hertz and I have another voltage source. This is at 60 Hertz. I cannot draw a phasor diagram between the voltage and current of this circuit and voltage and current of this circuit. The reason being that they are not in same frequency. So phasor diagram essentially means that they are at same frequency. Now here when we will discuss about the um this three lamp method, these two, this EF, that is the induced EMF of the incoming generator and the voltage of the infinite bus will have a small difference in frequency, and we will use this difference to draw a phasor diagram and find out the which one is at a higher frequency and which one is at lower frequency, and at what instant we have to close the circuit. So it will take at around 20 minutes more to explain. So we will discuss it in the next class.